Hello, today we're looking at section 9.4, compositions of transformations. A composition of transformations is where we perform two transformations on the same free image. So we take a figure, perform one type of transformation, and then use that image to then do another transformation. One type of composition is something called a glide reflection. A glide reflection is where you first perform a translation or a slide on a figure and then reflect it in a line parallel to the translation vector. The picture of the feet here is an example of a typical glide reflection. Imagine starting with the foot all the way on the bottom left here. If you were to take this and slide your foot forward for the glide along the translation, and then take that image where your foot is now and flip it over, so reflect it over this line parallel to your translation vector. So these two lines, the line of reflection and the translation vector, have to be parallel in a glide reflection. We can do a composition of any transformations. A glide reflection is just a certain type that has a specific name, but we can do transformations together of any type. So let's take a look at the first example. It says triangle GNC has these vertices. Graph the triangle and the image after this particular glide reflection. So we're going to start by taking triangle GNC, and first we're going to translate it along the vector -3, -3. That means that each of the coordinates, x and y, are going to move left 3 spaces and down 3 spaces, where we subtract 3 from both the x and the y coordinates. So point G was at 1, 1. G prime is going to end up at -2, -2. When we subtract 3 from each of n's coordinates, n prime goes to -1, +2. And when we subtract 3 from each of the coordinates for point C, C prime will end up at 1, -1. This is exactly what we did in a previous lesson. So now we plot our points just like before. And now we have triangle G prime, N prime, C prime. Each of the vertices was moved left 3 and down 3. But what makes this a glide reflection is that we're now going to use the points G prime, N prime, C prime and perform a second transformation. The second transformation is going to be a reflection in the line y equals x. If you remember from a previous lesson, this takes the coordinates of each vertex and switches the x and the y coordinates. So each point xy becomes yx. So now we're using the coordinates from G prime, N prime, C prime. And when we perform our second transformation, our new vertices are going to be called G double prime, N double prime, and C double prime. That indicates that it's the second transformation. So when I switch the coordinates from each one, G double prime actually doesn't move. N double prime goes to 2, -1, and C double prime will be at -1, +1. On the same graph, plot the points for G double prime, N double prime, and C double prime. Remember that for a point that doesn't move, we put this little slash and then the other name for the point. And here's our final image, our triangle after both the transformation and the reflection. Each of the transformations that we've talked about so far in this chapter has been in isometry. Remember, that means it preserves congruence. The preimage and the image are always congruent. When we do a composition of transformations, as long as each of the individual transformations is in isometry, the composition will be as well. And you can see that in the second example. Triangle cat has the given vertices. Graph the triangle and its image after a composition of, first, a rotation 180 degrees about the origin, and then a translation along the vector -2, 4. So if we take triangle cat and we rotate it 180 around the origin, remember from before, that takes each of our points, x, y, and changes their signs, -x, -y. So C prime should be at +6, +2. A prime will go to 5, 3. And T prime ends up at +2, +1. Graph triangle C prime, A prime, T prime. So here's our 180-degree rotation. These two triangles are still congruent. Now to perform our second transformation, we're going to use our new coordinates, C prime, A prime, T prime, and do a translation along the vector -2, +4. So each of our points, x, y, becomes x -2, y +4. In other words, each point is going to move left 2 spaces and up 4 spaces. So now to find the coordinates C double prime, A double prime, T double prime. I actually like to do all the x coordinates first. So just in my head, I know I'm subtracting 2 each time. So 6 minus 2 makes the first one 4. For A double prime, 5 minus 2 makes its x coordinate 3. And T double prime, 2 minus 2 makes its x coordinate 0. Then I like to do all of the y coordinates. So now I'm adding 4. So C double prime will have a y coordinate of 2. 3 plus 4 makes A double prime's y coordinate 7. And 1 plus 4 means that T double prime will have a y coordinate of 5. Graph this triangle now. And as you can see, all 3 triangles, our pre-image, its image, and then our final figure are all congruent. So the composition of our rotation and our translation is in isometry. When you flip over to the back of the notes, the next 2 examples are going to be a little tricky on the digital notes like we've done before, but we'll get through it. You guys did really well with the other ones. So the next example looks at what happens if you reflect an image over 2 parallel lines. The composition of reflecting over 2 parallel lines is the same thing as performing just a translation. When you reflect over 2 parallel lines, it's equal to a translation twice the distance between those 2 parallel lines. So if you look at the image where they've done this for you, They started all the way on the left with triangle P. They reflected triangle P over line K, and that gave us triangle P prime. They then took triangle P prime, reflected it over line L, and ended up with this final image, P double prime. The idea here is that performing those two reflections is the same thing as if we had just taken our original triangle P and slid it over, translated it, to end up with triangle P double prime. That translation is along a vector twice as long as the distance between the two parallel lines. So if you take a look at the next example, it says reflect figure S in line M and then in line P. Describe the single transformation that would map triangle S onto triangle S double prime. So if you remember from a previous lesson, when we perform a reflection over a line, so I'm going to focus first on just triangle S and line M. In order to reflect this triangle along line M, or across line M, we're going to start by drawing our perpendicular lines through each vertex. So here I'm going to do my best to freehand lines perpendicular to the line of reflection through each vertex of the triangle. Then you would take your ruler, you measure the distance between each vertex and the line of reflection, and you recreate that distance on the other side of the line of reflection. Okay, again, I have to sort of eyeball this on my iPad, but triangle S double prime, S prime, should look something like this. Now we're going to take triangle S prime and reflect it over the second line, reflect it over line P. So again, we would start by drawing our lines perpendicular to line P that goes through each of the vertices of triangle S prime. Again, we measure the distance from line P to each vertex, and then we recreate that distance on the other side of line P. As you can see, my picture is definitely not perfect. Let me see if I can adjust that a little bit. Okay, that looks a little better. So here's triangle S double prime. Imagine if you could have taken triangle S and just slid it over, skipping all of these reflections, and just slide it over to get triangle S double prime. So having done these two reflections is the same as just doing a translation, a slide, along a vector that would have been 3 inches long. And I know that even on your papers, the measurement is not the same. I got that 3 inches because remember the translation that is the same as doing those two reflections is twice the distance between the parallel lines. So that 1.5 inches on the question is to give you the length of the translation vector. Okay, our last example for today is a composition of two reflections again, but this time the reflections are going to occur in intersecting lines. Performing two reflections over intersecting lines is the same as just doing a single rotation, and that single rotation is done for twice the measure of the acute or right angle formed by your intersecting lines. The process for the last question is going to be very similar to the one we just did. We're going to reflect triangle S first over line M, then over line P. But because these two lines are intersecting, those composition of reflections is not going to be the same as just having slid the picture over, but instead rotating the picture. And the angle of rotation is twice the number of degrees where the two intersecting lines meet up. So let's start by trying to perform our reflections. So if I start with triangle S, I want to create my lines perpendicular to line M that pass through triangle S. As you can see, the ones I'm doing by hand aren't so perfect. Let me see if I can adjust that again. Okay, once you draw your perpendicular lines, you measure the distance from line M to each vertex, and then you recreate that distance on the other side of line M. I drew this on paper before I did this video lesson, so I'm partially trying to recreate what I have on my paper to make my picture a little more accurate. Okay, this gives us the figure S prime after we've reflected over line M. I'm going to get rid of my perpendicular lines here just so that the picture doesn't get too crazy when I perform the next reflection. So let me finish getting rid of these. Okay, now we're going to take triangle S prime and we're going to reflect it over line P. So once again, we're going to draw our lines perpendicular to line P through each of the vertices of triangle S prime. Okay, then we measure the distance from each vertex to the line of reflection. Recreate that distance again on the other side of the line of reflection. Let's put this about here, make it look more accurate. Okay, this final triangle that we come up with is triangle S double prime. And the point of showing this is to show you how, if I had just taken triangle S and rotated it 100 degrees, and remember rotations are always counterclockwise in math unless otherwise specified. If I took triangle S and rotated it 100 degrees, it would end up in the same position as triangle S double prime. So the single transformation that maps S onto S double prime is a rotation 100 degrees. And that's twice the measure of the angle formed by those two intersecting lines. Do the best you can, please, drawing these different compositions that are not on the coordinate plane in your homework. Please make sure as you're doing your homework, for the questions that are on the coordinate plane, you need to show the coordinates of each point. You're not going to get full credit for just graphing. I want to see all of this work in between, like I've shown you here in the video lessons. Have a great day. If you have questions, please post them under the comment section of Teams. Talk to you tomorrow.